Okay, so we want to look at eigenvalues and eigenvectors of a square matrix, right? Okay, so if I have, for example, I have a 2 by 2 matrix A, which is this 2 by 2 matrix. I'm using this as an example. So this matrix here, 0, 1, 1, 0, right? Now let's consider a linear transformation from the plane to the plane defined as TV is equal to AV, right? So what I'm doing is I'm taking my domain vector V over here and I'm multiplying it by the matrix A. And the matrix A that I'm using in this example is the 0, 1, 1, 0, right? Okay, so we saw previously that this sort of definition here of, this defines a linear transformation. And because of the size, I'm looking at a 2 by 2 matrix. This is a linear transformation from the plane to the plane, right? Right, so we can actually visualize what this linear transformation is, right? These blue vectors over here are actually the domain vectors, and the green vector over here is the corresponding image, right? When I change the vector in the domain, I get a different image vectors, right? Okay, so if I have a linear transformation defined this way as TV is equal to AV, right? What an eigenvector of your matrix A is going to be is an eigenvector of a matrix A is a vector in the domain um, that when you apply this map to that vector, the direction of the vector doesn't change, right? And by direction, I can mean positive direction, and well, the direction could reverse, right? But the vector would still lie along the straight line, right? So here you see in a definition here, V is an eigenvector for your matrix A, right? If TV, and in this case, TV is equal to A times V, right? If this matrix A times V is basically is equal to V and up to a scalar here, lambda, right? So it's AV basically gives you the same vector V, right? But adjusted by the scalar over here, right? So if I can find a vector V that such that A times V is really just a scalar multiple of V, then this vector V here is an example of an eigenvector, right? And the scalar over here is called an eigenvalue, right? Okay, so again, we're looking at this matrix A over here, which is 0, 1, 1, 0, right? So let's see in this software over here if we can identify what the eigenvectors are, right? Okay, so this over here, well, this vector over here is not an eigenvector, right? Because if you look at the image here, this green vector here is not lining up with your vector V here, right? If, however, so I can try moving this around, right? And we'll see in a while a systematic way to get the eigenvectors, right? If, for example, I have and with these little boxes over here, this would indicate that it's say vector. These would be the x components of a vector, and this would be the y components of a vector, right? So what you want to notice is that if the x component is actually equal to the y component, right? You notice that okay, so over here, this vector v, the image is not the same, right? The green vector is different from the blue vector. Green vector is vector, image vector, and blue vector is the domain vector, right? And so in this case, this v over here, as it is right now, is not an eigenvector, right? But what you want to notice is if I move it so that the vector v actually lines up with the vector v is parallel to 1, 1, right? What you want to notice is that the blue vector and the image vector actually line up, right? So that means that your vector v that you had was eigenvector, right? Okay, so this particular vector, what you want to notice is that the eigenvector the x component is equal to the y component, right? And what we will see is that, okay, so next thing you want to notice is that it works for example, say if I have x component equal to y component over here. So this is if you want a vector 4, 4, right? If I use a larger vector here, but the x component is still equal to the y component, you want to notice that is also an eigenvector, right? Okay, now what I'm seeing over here is that your eigenvectors, one set of eigenvectors basically is going to lie along this line, y is equal to x, right? Or be a multiple of your vector 1, 1, right? Okay, so, and we'll see in a second that 1, 1 is an eigenvector of this matrix A, which is 0, 1, 1, 0, right? Okay, but let's keep looking. We want to see in the software we can find a next eigenvector, right? Okay, so, well, that's not going to be an eigenvector there because the image AV is not the same as V, right? Likewise, this is not an eigenvector, right? Now, what I had before, the example that I had before is a vector parallel to 1, 1, right? If, for example, I use now 1 minus 1, which is a different uh, direction, right? What you want to notice is that this vector in the direction 1 minus 1, this is also an eigenvector, right? Because, well, what's the image, right? The image, notice the image vector over here is actually lining up with the vector v from your domain, right? Okay, even though it's, well, it's in exactly the opposite direction, this v over here is still an eigenvector because your image vector, right? Your image vector AV is actually a multiple of your starting vector v, right? In this case, the multiple is a negative multiple, but it's still just a multiple, right? Okay. All right, so let's look at the formal definition, right? So I have a n by n matrix, right? We're looking at n by n real matrix. That's what we're restricting ourselves to in this class, right? Okay, so if I have a n by n matrix, a square matrix, then a vector v is an eigenvector if AV is equal to lambda v, right? So as I said, if you have your vector v and you multiply it by a, your resultant vector, right, is parallel to the starting vector v, right? Okay, right. So this is what an eigenvector is. An eigenvector is a vector v that satisfies this condition over here, right? AV is equal to lambda v, right? A times the vector v is parallel, the image AV is equal to lambda v, right? So that means that your lambda v over here is parallel to your starting vector v, right? Okay, right. So this is what an eigenvector is, right? And if you have AV is equal to lambda v, right? So for your particular eigenvector v over here, you're going to have some scalar multiple of v, right? And the scalar out in front there is the eigenvalue associated to the eigenvector, right? Okay, and you denote that eigenvalue as lambda, right? Alright, okay, and we found in our software here that for your matrix 0, 1, 1, 0, that a vector that is parallel to 1 minus 1 would be an eigenvector for your matrix A, right? But let's check that, right? So I have this matrix A over here, right? And I want to work out AV, right? Where V is the vector 1 minus 1, right? Okay, so if I have A times V, right? So this is my A over here, and the vector V that I'm using is 1 minus 1. If I do this matrix multiplication over here, I get minus 1 over here for X component and 1 for the Y component, right? Okay, so what I get isn't the same as the 1 minus 1, but it is the same up to a scalar multiple, right? You want to notice that this minus 1, 1 is equal to the 1 minus 1, right, times a minus 1, right? So if you notice here that this is the A over here, this is the V, which is 1 minus 1, and that's equal to minus 1 times the original V, which is 1 minus 1, right? Okay, so here for this V over here, which is your 1 minus 1, this V is an eigenvector, and associated eigenvalue is minus 1, right? Alright, okay, so for this same matrix A over here, let's see if you can get a second eigenvector, right? That's not parallel to this 1 minus 1, right? Okay, so I'm gonna use, let's try this 1, 1 over here, right? Which we found from the software, right? So if I work out A times V in this case, right? So A is the 0, 1, 1, 0, the V is 1, 1, right? When I do the matrix multiplication, I work out the AV, I get 1, 1 over here. And you want to notice this is it's the same as, well, it's literally the same as the vector V that you started off with. And you can write this in the form lambda times V. In this case, the scalar lambda is equal to 1 over here, right? Okay, so what I have is AV is equal to lambda V when the lambda is equal to 1, right? So your 1, 1 over here, this 1, 1 over here, by definition, is an eigenvector for your matrix A here, right? And the eigenvalue is your scalar here, right? So I have this written in the form AV is equal to lambda V. So this is the original V, this is the original V, this is the scalar. In this case, the scalar is 1, right? So your eigenvalue associated to the eigenvector 1, 1 is equal to 1, right? Alright, so really, so this matrix A over here, right? What I really did to find these eigenvectors, I didn't show any working to find the eigenvectors, right? One eigenvector was 1 minus 1. And the next eigenvector was 1, 1, right? Okay, so how do you actually find these eigenvectors and the eigenvalues, right? Well, how you do it is you actually find the eigenvalues first, right? And then you find the corresponding eigenvectors. So that's your systematic way of doing it, right? And how you find your eigenvalues is via something called characteristic polynomial, right? Okay, so what a characteristic polynomial is, right, is given a matrix A here, right, given you a square matrix that you want to find the eigenvalues for, first of all, right, what you do is you construct this object, which is determinant of lambda I n minus A, right? So remember, A is n by n matrix, right? So what you're going to do is you're going to take your A over here, take an identity matrix of the same size, multiply that by a variable, which in the variable we're going to call lambda over here. And we construct this quantity lambda I n minus A, and then you take the determinant of that, right? Okay, so let's see an example of obtaining a characteristic polynomial associated to a square matrix A over here, right? So the example that I'm using is the example matrix that I had before, 0, 1, 1, 0, right? And what I'm going to do is I'm going to form this matrix over here, lambda I2 minus A. Notice this 2 over here, it's a 2 by 2 identity. And this matrix here is the same size as your given matrix that you're working with, which is a 2 by 2 in this case, right? Okay, so I2 is this identity matrix over here. This A over here is your original matrix A. You have your identity here and you multiply it by the scalar lambda. So this over here is your lambda I2, right? So you have your lambda I2 and you're subtracting A, right? So this is lambda I2 minus A. And then what you're going to do is you're taking determinant of that. Remember, that's what these large vertical lines mean over here, right? That you're taking determinant, right? Okay, so to work this out, first you need to do your scalar multiplication and the matrix subtraction over here on the inside. When you do that, you're going to have a lambda over here, and then you would subtract, right? So you have lambda here, subtract 0 to get lambda here, subtract 1 here to get minus 1, subtract 1 over here to get minus 1, and then you have a lambda over here, right? Okay, so this object over here, this is lambda I2 minus A, right? And I actually wrote it down separately, right? So for your matrix A over here, this is, in this case, this is lambda I2 minus A, right? It's a matrix with lambdas on the diagonal, right? Notice you're not going to have any lambdas anywhere else, right? The lambdas would only lie on the diagonal here, right? Because this matrix A didn't have any lambdas to start off with anyway. And the only place where the lambdas are going to come from is going to come from lambda times identity matrix, right? And so, well, the lambdas are just going to lie on the diagonal, right? So once I have this lambda I2 minus a, what I'm going to do is, well, I need to take the determinant of it in order to find my characteristic polynomial. Alright, so the determinant of this matrix, we just use for these examples, and so it's probably not a good idea to use, say, like row reduction or so, because of the variables. It might get somewhat confusing. So because these are relatively small examples, we just use this by using a calculate determinant by using a cofactor expansion, right? And in this case, it's pretty simple, right? This is a 2 by 2, so you multiply lambda times lambda, and then you subtract minus 1 times minus 1, right? So you get lambda squared minus 1, which is this over here, right? Okay, so this is your characteristic polynomial, right? And this is what you use to get your eigenvalues of your matrix A, right? How you get your eigenvalues of your matrix is you take a characteristic polynomial and you set it equal to 0, right? Okay, so just a little bit of notation. The determinant of the lambda I2 minus a, that is a characteristic polynomial, right? When you take your characteristic polynomial and you set it equal to 0, what you get is a characteristic equation, right? Okay. Right, so I have, in this case, the characteristic polynomial was lambda squared minus 1, and I set that equal to 0 to get my characteristic equation. And what your eigenvalues? You get your eigenvalues by solving this equation, right? Or more formally, the eigenvalues of your matrix are the roots of this characteristic equation, right? And it's not hard to solve this. You're going to see you get 1 and minus 1, right? And you want to recall those are the eigenvalues that we found before, right, by our ad hoc methods for matrix A. One eigenvalue was 1 and the next eigenvalue was minus 1, right? But this over here, this is a systematic way of finding your eigenvalues, right? What I'm trying to do is I'm trying to solve to get the eigenvalue corresponding to lambda is equal to 1. I'd need to solve this vector equation here, right? AV is equal to minus 1v, right? Okay, so let's notice some things about this. AV is equal to minus 1v, right? This over here, this vector v on your right hand side, right? I can always write it as identity, right, times v, right? You'll see in a second why I'd want to do this, right? So I have your vector v over here, and I can write that as identity times v, because identity times any matrix is just going to give me back the same matrix. In this case, the matrix or the vector, well, more precisely, the vector is v here, right? So the identity matrix times the vector will just give me back my vector, right? Okay, so I write this v over here as identity times v, right? And what I do now is I bring this av over here onto the right hand side and I factor out the v, right? Okay, now given this matrix equation, I can rearrange it like this, and I can also rearrange it so I can get this third form, right? And likewise, if I have this third form, I can go back to the second form and go back to the first form, right? So what that means is that these three matrix equations are equivalent, right? That's what these two-sided arrow means, right? The statement is true if and only if the statement is true, right? Okay, so which means that solving for the vector v over here is the same as solving for the vector v here, right? Now, while this may look a little sort of convoluted, right? What you want to notice is that what I have over here is inside over here is, and remember this minus 1 is an eigenvalue, right? So this over here is basically lambda I2 minus a. So it's basically the same lambda I2 minus a when the lambda is equal to minus 1, right? So the point is this expression over here, right? the minus 1 I2 minus A. I can really just get from the lambda I2 minus A by putting in lambda is equal to minus 1, right? And when you're doing these calculation by hand, right, it's sort of useful shortcut if you want in your working, because you would have worked out what this is already, right, to get your characteristic polynomial to get your eigenvalues, right? Okay, so let me just, over here, what I did is I just wrote out everything, right? I just put in the information for the this third expression here, right? So the 0 here is this 0 vector here, right? The I2 is the identity matrix here. It's being multiplied by minus I1, and this is minus A, right, times your vector V, right? And the vector V I wrote as x1, x2, right? Notice here the vector V is unknown, right? So what I'm trying to do is I'm trying to solve for the vector V. So I'm trying to figure out what the x1, x2 is over here, right? Okay, so one more time, 0 over here is this 0 over here, right? I have minus 1 times I2, which is this minus 1 I2, and then minus A, which is this minus A over here, right? Okay, and this simplifies down when I could just, well, multiply this out and multiply the scalar here by this matrix, and then subtract my matrices, and I'd get minus 1 here, minus 1 here, minus 1 here, minus 1 here, right? And what do you want to notice? Okay, so if I'm trying to determine the eigenvector V, right, I start with this matrix equation over here, which is the definition, if you want, for getting my eigenvector from my eigenvalue. But really it helps to rearrange it in this form. Why it helps to rearrange it in this form is you already have this expression, lambda I2 minus A, right? And you want to notice over here, right, you could have actually really just jumped to this step by just putting in lambda is equal to minus 1, right? Because if you put minus 1 in here and minus 1 in over here, right, you'd in fact get this matrix minus 1, minus 1, minus 1, minus 1 here, right? Okay, so if you're trying to get the eigenvalue for lambda is equal to minus 1, you could really sort of just skip this working over here, right? Put in lambda is equal to minus 1, put in your eigenvalue, which is minus 1, minus 1 into this, and then just form this matrix equation, right? And what we're going to see in a second is there's actually a somewhat faster way, right, to do this, right? Okay, so I have this matrix equation here, right? And what I can do is, right, so I have this matrix equation, and to find an eigenvector means I want to find a non-zero x1, x2 that is a solution of this matrix equation, right? Right, so let's recall something that we saw in lecture 9, right? You could always take a look at lecture 9 to review, right? And what we're talking about here is null space of a matrix, right? Okay, so if I have a matrix, right, what your null space is going to be, right? Null space of this matrix B is the solution set of this matrix equation here, Bx is equal to 0, right? And what you could do is you can multiply out your matrix equation over here, and what you're going to get is a homogeneous system, right? Here what you're doing is using a column vector with x1, x2, x3, and x4, right? And when you multiply this out, you're going to get a homogeneous system, right? So your null space is a solution set of this homogeneous system, or if you want, a solution set of this matrix equation, right? Now, how do you do this, right? To get your null space of your matrix, you form your homogeneous system, and then you form your corresponding augmented matrix, right? But you want to notice that this matrix over here, this 2, 8, 4 minus 2, 3, 7, 5, 6, is really just the same as the matrix that you had to start off with, right? So I didn't really need to go through this step over here, right, of really writing out explicitly what the homogeneous system was, right? What I could have done is just from this, the matrix B that was given to me, if I'm going to get a null space, I just directly form this augmented matrix here, right? And also you want to notice that these zeros here, and I believe we talked about this in lecture 9, right? You don't really need these zeros over here, because when you do your row operations, zeros, this column over here would always just remain 0, right? So this over here is redundant information, right? So if you find a null space of matrix B, right, really you could just start with this matrix over here, and this matrix on the left hand side here of your vertical line is really just the B that you were given in the first place, right? Okay, so this is your B over here, and with this B, what you do is you apply a Gauss Jordan to your B. Right, now when you apply a Gauss Jordan to your B, you will get an RREF over here, right? And with this RREF, you form your associated system. And then the solution set for this system is going to be a null space of your given matrix. And remember, the null space of your given matrix. The given matrix in this case is this over here, right? Okay, so if one more time, if I want to get a null space of this matrix B, right? While I could construct your matrix equation over here, right, and form your homogeneous system, form the augmented matrix and so on, and start from there, right? What you could do is you could just take your matrix B that you want to get a null space of, right? Just take that and directly apply Gauss. This is your matrix B over here, right? Your matrix B, and then just apply Gauss Jordan to this RREF. Form your associated system. Right, you form your associated system over here, and then from this associated system you get your solution set, right? And you can write your solution set. Next thing that is useful to know is that once you have your solution set expressed in terms of your free variables, right, you could always rearrange the solution set so that you get it as a span of vectors here, right? Notice here I have the span of these two vectors, minus 6, 5, minus 1, 5, 1, 0, and minus 31, 1, 5, 9, 1, 5, 0, and 1, right? Okay, so this method of obtaining null space is particularly useful for us when we get in eigenvectors, because when we actually calculate in eigenvectors, what we're doing is we determine a non-zero vector in a certain null space, right? So we're looking for solution vectors that actually look like this over here, but in the context of eigenvectors. So given what we just saw, right, what we're doing over here for your matrix minus 1, minus 1, minus 1, minus 1, right? Finding an eigenvector, right, which is going to be this x1, x2, a non-zero solution of this matrix equation, is really just finding a vector in the null space of this matrix over here, right? Okay, so we want to get, and I state this over here, right? So an eigenvector for your eigenvalue lambda is equal to minus 1, right? What you're doing is, remember how I got this minus 1, minus 1, minus 1, minus 1, right? I put minus 1 as the eigenvalue into the expression lambda I2 minus a, right? Okay, so, and I just said that an eigenvector corresponding to lambda is equal to minus 1 is a non-zero solution of this matrix equation, right? Which is a non-zero vector in the null space of this matrix over here, right? So I can summarize what I said before, right? That an eigenvector for corresponding to eigenvalue lambda is equal to minus 1 is a vector in the null space of this matrix over here, right? So what you do is you take your lambda I2 minus a, right? You put minus 1 into it, so you get this matrix, and your eigenvector is really a null space, is a non-zero vector in the null space of this minus 1 I2 minus a, which is this matrix over here on your right hand side. You need to determine the null space of this matrix, and as we just saw in my little review for null spaces, is given this matrix here that you want to get a null space of, all you can do is you just take this and you apply Gauss Jordan to it, right? Form your corresponding system here, right? In this case, the corresponding system is pretty easy, right? And you can see that a non-zero solution for this system here is when x1 is equal to 1 and x2 is equal to minus 1, which is this 1 minus 1, right? Okay, so this vector 1 minus 1 over here, right, is a solution of this system over here. And this system over here was formed from this matrix equation. Notice the 1 minus 1 satisfies this matrix equation when you multiply it out. And this matrix equation over here is actually coming from this form minus 1 I2 minus A times V. And this over here is equivalent to that AV is equal to minus 1V, which is really a definition for eigenvector corresponding to eigenvalue lambda is equal to minus 1, right? Okay, so what I found over here, 1 minus 1 is an eigenvector corresponding to the eigenvalue lambda is equal to minus 1, right? Right, so one more time, if I want to get the eigenvector corresponding to eigenvalue lambda is equal to minus 1, what I could do is, in this expression for lambda, I2 minus A, I can substitute minus 1 into it, right? And when I substitute minus 1 into it, I will get this matrix here, minus 1, minus 1, minus 1, minus 1. And obtaining an eigenvector for lambda is equal to minus 1 is obtaining a non-zero vector in the null space of this matrix, right? Okay, so now let's use that same sort of idea to get an eigenvector for the eigenvalue lambda is equal to 1. Notice this is now a different eigenvalue, right? Okay, so the method that I would use is for this expression lambda I2 minus A. Now what I'm going to do is I'm going to put 1 into it, right? And when I put 1 into it, I'm going to get 1 minus 1 minus 1, 1, which is this matrix over here. And now what I want is the eigenvector is going to be a non-zero vector in the null space here, null space of this matrix. Okay, so I need to get the null space of this matrix, and to get the null space of this matrix, I just apply Gauss-Jordan to it, right? Form the associated homogeneous system here, right? And this associated homogeneous system, it's clear that non-zero solution for it would be when x1 is equal to 1 and x2 is equal to 1, right? So this solution vector over here, 1, 1, right? This is an eigenvector corresponding to the eigenvalue lambda is equal to 1, right? Right, okay, so let's see an example of calculating eigenvalues and eigenvectors and corresponding eigenvectors for now a 3 by 3 matrix here, right? Okay, so when you're doing this, first thing you'd want to do is you want to get the eigenvalues, right? And the eigenvalues, and in order to get the eigenvalues, you need the characteristic polynomial first, right? So the characteristic polynomial is the determinant of lambda I3 minus A, right? I3 is 3 by 3 identity over here. You're multiplying it by this variable lambda. You're subtracting A, and you're taking the determinant of that, right? So first you want to work out what the lambda I3 minus A is, right? And I do that over here. Notice you're going to have lambdas on your diagonal, right? Okay, and then you're subtracting your matrix here, right? One sort of fast way to construct this lambda I3 minus A is you just put this on your diagonal, right? And then whatever your entries are for your matrix A, right, you just put them into corresponding positions, but you just put the negative of them, right? Okay, so for example, this 1 in your first row and third column, that would give you a minus 1 in this first row and third column. This 2 over here would contribute minus 2 over here on the first row and first column, right? Okay, and once you have this lambda I3 minus A, you take the determinant of this, right? As I said, we don't want to use row operations to do this, so we're just going to use a cofactor expansion. In this working over here, what I have is expanding along your first column over here, right? So you're going to get lambda minus 2 times this the determinant of this 2 by 2 submatrix, 0 times the determinant of a 2 by 2, and then minus 1 times the determinant of a 2 by 2, right? Right, okay. So you work it out, and when you expand out everything, what you end up with is you end up with this cubic over here, right? And your cubic here, you want to factor, right? In this class, the eigen values that we're going to look at would be most of the time they're going to be real, so this would be easy to factor. But you all should know how to do this. This is a cubic, and you factor this. You could use remainder theorem, right? Okay, to factor it, right? You put in a value, you find a value, and you see, well, what value would give you 0, right? And for example, if I put 1 into this, I would get 1 minus 3, which is minus 2, minus 1, which would be minus 3, plus 3, which would be 0, and that would mean that lambda minus 1 is going to be a factor, right? So you factor the lambda minus 1, you'd be left with a quadratic, and then you factor that quadratic, right? Okay, but that you should know how to factor a cubic. At you would have seen that back in sixth form. All right, so once I have this cubic over here, right, and it's factored like this, then I set it equal to 0, and solutions over here would be my eigenvalues, right? So in this particular case, the eigenvalues would be minus 1, 1, and 3, right? Okay, so as before in the case of my 2 by 2 matrix, first thing you do is you find your eigenvalues, right? And now once you find your eigenvalues, for each eigenvalue you want to find corresponding eigenvectors, right? Alright, remember what I did in the 2 by 2 case, right? Once I had this lambda I2 minus a, and I wanted to get, say, an eigenvector corresponding to lambda is equal to 1, I put the 1 in for lambda over here, right? And when I put the 1 in, I would get a certain matrix, and then all I do now is I get a non-zero vector in null space here, right? So likewise with your lambda I3 minus a here, right? What you do is you put the lambda is equal to minus 1 into it, right? And put in the lambda. Right, so you could put the lambda equal to minus 1 into here, right? And that would give you, so you see, already have an expression here for lambda I3 minus a inside here, right? So if I put lambda is equal to minus 1 into this, I will get minus 3, which is this minus 3 here. I'd get minus 1, which is minus 1, right? In other words, you want to notice I'm going to get basically the same thing as this over here. The only thing I really need to do is just worry about diagonal entries, right? So putting in lambda is equal to minus 1 would give me minus 3 here. Lambda is equal to minus 1, and then minus 1, which is minus 2, right? Okay, so this is the lambda I3 minus a when the lambda is equal to minus 1. And now with this over here, the eigenvector and eigenvector corresponding to lambda is equal to minus 1 would be a non-zero vector in your null space of this matrix here, right? Okay, so to get the null space of this matrix, what you do is you apply Gauss-Jordan to it, right? In this work in here, right, I actually put the zeros in because remember, by getting null space, what you're doing is you're looking for non-zero vectors in a matrix equation, right, and associated linear homogeneous system. So I can write the 0 vectors over here, although they don't really do anything for me. Anyway, so apply Gauss-Jordan to that, right? And then with this RREF, you're going to get an associated system, right? And a non-zero solution to this system would give me an eigenvector corresponding to lambda is equal to minus 1, right? So what I want to get is I want to get a non-zero solution to the system. Now to get the solutions for the system, you do it in your normal way, where you express your pivot variables in terms of your free variable, like I did over here, right? And here what I have is that the x1 is equal to 0, x2 is equal to minus 3, and x3 is equal to itself, right? Okay, and here I can factor out the x3. This is a column vector, right? Note the transpose over here, right? Okay, so one possible eigenvector here corresponding to lambda is equal to minus 1 is 0, minus 1, 1, right? And that's what I have over here. 0, minus 1, 1 is an eigenvector corresponding to eigenvalue lambda is equal to minus 1, right? And similarly, to get an eigenvector corresponding to lambda is equal to 1 now, right? What you're doing now is you consider in the matrix 1 times I3 minus a. So this is your lambda I3 minus a inside over here. You put in 1 in now, right? And as I said before, it's really a diagonal entries here that are going to change according if you change the lambda. So here I'd get 1 minus 2, which is minus 1, right? I'd get lambda is equal to 1, which is 1 here. I get 1 minus 1, which is a 0 over here. The off-diagonal elements remain the same, right? So the 1 I3 minus a I can determine from this lambda I3 minus a by using lambda is equal to 1. And now an eigenvector v is corresponding to lambda is equal to minus lambda is equal to 1, right? Is going to be a non-zero solution for this homogeneous system, and this is your augmented matrix associated to this homogeneous system. Apply Gauss-Jordan to it, right? Form your associated system to the RREF that you get after applying Gauss-Jordan, right? A non-zero vector is a non-zero eigenvector is a non-zero solution of the system here, right? Okay, and you do this in your normal way, right? You express your pivot variables in terms of your free variables. In this case, what you're going to get is x1 is equal to minus 2x3, x2 is equal to x3, and x3 is itself because it's free, right? I can factor out the x3 over here, and I see that minus 2, 1, 1 is a solution for the system. And because it's a solution for this system over here, it's in fact a solution for this matrix equation here, right? And it's a non-zero solution for this matrix equations, and this matrix equation here, non-zero vector solutions would give me eigenvectors for lambda is equal to 1, and therefore what you have is minus 2, 1, 1 is an eigenvector corresponding to eigenvalue 1, right? And so that's how you get the eigenvector corresponding to eigenvalue is equal to 1. And similarly, to get eigenvector corresponding lambda is equal to 3, you're going to do similar working, right? So you can take a look at the notes. The working is really just the same as the previous two cases of the eigenvalues. Lambda is equal to minus 1 and lambda is equal to 1.